Hello students, and welcome to section 3.5, exponential and logarithmic functions. As a warm-up, we're going to go ahead and solve each of the following. So let's take a look. Log base 2 of 8 plus 2 log base 2 of x squared plus 7x equals 9. We've done problems like this in the past. Very first thing to recognize is that we do have logs of the same base. And we happen to have a log base 2 of 8, which is something you can simplify really without a calculator, asking yourself 2 to what power is equal to 8. As we continue, of course, that ends up being 3. That first one, 2 to the third, of course. And the second one, I just left as is for the moment. In the next step, you can simply go ahead and subtract 3 from both sides. So if you do that, you'll end up with 6 on the right side. And on the left side, still 2 log base 2 of x squared plus 7x, and that equals 6. Divide both sides by 2. And in the next step, you'll have log base 2 of x squared plus 7x equals 3. You can rewrite a log as an exponential. So 2 raised to the third power, and that, of course, is equal to x squared plus 7x. 2 to the third is, of course, 8. Which if you subtract, you end up with this quadratic set equal to 0, which ends up being a factorable quadratic as such. X minus 1 and x plus 8 equals 0. And then, of course, we can go through the process of setting each equal to 0. And if you do that, you'll end up with x equals 1 and x equals negative 8. I do urge that you double check your answers to see if, in fact, you get both to be correct. In other words, if you plug in 1 here, 1 squared plus 7 times 1, that's 1 plus 7, which of course is 8. So you can take the log base 2 of 8, okay, which of course ends up being, what, 3. So you have log base 2 of 8, which is 3. 3 times 2, which is 6. 6 plus 3, of course, is 9. If you plug in negative 8, what do you get? You get negative 8 quantity squared, which is 64. And then you have 7 times negative 8, which is negative 56. 64 minus 56, of course, is 8. And if you do the math, you get the same result. You'll get 9. So the answers both check. Please be very careful when checking negative answers, for example, that you end up getting an answer that, in parentheses, for example, is either is positive in general and not, I should say, either negative nor 0. It has to be a positive number because you can't take the log of a negative nor 0. Number 2, we have got 5 plus 2e to the 2x times e to the 5x plus 1. This little denotation here suggests that because my bases are the same here and here, e, I can add my exponents. Multiplication of things that have the same base, or terms that have the same base, demand that you add exponents. If we do that, and of course also note that I can subtract 5 to kick the problem off. Trying to get x by itself, we're going to get there by subtracting 5, and like I said, adding your exponents such that 2e to the 7x plus 1, 2x plus 5x plus 1, of course, is 7x plus 1, and that equals 20. Divide both sides by 2, and when we do this, we end up with e to the 7x plus 1 equals 10. And then now it just becomes a matter of rewriting it as a natural log or taking the natural log of both sides. I'd rather write it as a natural log such that natural log base e of 10 is equal to 7x plus 1. Now we can type in natural log of 10 on our calculator. You can then subtract 1 and you can divide by 7, which if you do, you'll end up with the final answer as such. So again, natural log of 10 minus 1 divided by 7, and 0.186 is the final answer. Let's move on to the intro for today. The 5 most common types of mathematical models involving exponential and logarithmic functions are as follows. We have an exponential growth function, unconstrained population growth as an example, and then y equals a times e to the bx power, where b is greater than 0. And we've seen exponential growth functions quite a bit already. Exponential decay models, for example, carbon dating, take shape where this is your equation, y equals ae to the negative bx, where b is again greater than 0. Or another version that is more kind of commonly viewed as in various contexts is y equals ae to the bx, where b is negative when it's all said and done. We can start it with negative in the front of the exponent, or we can not have the negative but call b negative when you actually do your assessment. Gaussian models, normal distribution, we use this in probability and statistics. Here's the equation. You don't have to memorize this. Logistic growth, constrained population growth is an example. Here's your equation. You don't have to memorize that either. Logarithmic models, magnitudes of earthquakes, for example, y equals a plus b natural log of x, or y equals a plus b log of x. These are equations that you probably will have to have memorized, but they're really not too complicated if you consider the ideas of, working with something like this, for example, wherein you have a number added to it, multiplied to the log, and you could easily see some other parts of the expression vary based upon what x is being added to in parentheses or subtracted to in parentheses. The models that we see here, this Gaussian model graph, you should have a general idea that it's going to take this shape thanks to this equation. Logistic growth takes this particular shape. And then lastly, you already know log models take shape accordingly, as we know logs to be the inverse of exponentials. Okay, so let's move on to the next page. Exponential growth and unconstrained population growth. The population P of a city is given as follows. P of t equals 19,995 e to the kt, where t represents 2,000. T equals 0 represents 2,000. In 1945, the population was 9,253. Find the value of k and use this value to estimate the population in the year 2020. Okay, this problem was written a while ago, so let's see how we're looking here. Okay, the year 2020 is now. So if we go ahead and start the process, noting that t equals 0 again is 2,000, that means negative 55 would be 1945. If you kind of go back in time, we don't typically look at negative t values, but in this case, because we're relating what we're given and what we have to go back to in 1945, t would actually have to be negative in context. And that's going to be okay in our problem here, as we're about to find out. It continues as such. So if you use the equation up above, so plugging in 9,253 in for P of t, again knowing the original value of what, 19,995 at the year 2000, times e to the k times negative 55. So here, if you haven't already noticed, we have everything but k. We don't know how the population is growing. All we know that it is growing over time. So let's calculate this. We divide both sides by 19,995, and we get that value, 0.4627. It's still set equal to e to the negative 55k power. Here we can go ahead and take the natural log of both sides, or we can rewrite it as a natural log. So what? Natural log base e of 0.4627 equals now this exponent of negative 55k. This decimal, natural log of 0.4627, and I can get my calculator opened up here in a moment. We can see how the calculator frames up, and the value, of course, exactly frames up. Divide that by negative 55, and we get 0.014 for k. So this decimal, 0.014, is positive, which is a good sign. It indicates that your population is growing, not decaying over time. And then you can go ahead and, because it asks you to not just find the value of k, use this value to estimate in the year 2020 the population. So using the exact same equation, so P of t equals 19,995 e to the, again, 0.04 times 20 power, because we have, again, t equals 0. So in the year 2020, t would be, well, 20. We do the math, and in the year 2020, this population should be approximately 26,461. A couple things just to highlight when we've done this in the past. When it comes to rounding in particular, which you should be very mindful of, rounding is an important aspect of, obviously, all of your analyses. And that will require, when I do type in, for example, we go ahead and we type in, let's scoot this over a bit, pull this over. If we can go back and find our, let's say, k value, let me just show this, 9253 divided by, 19995, that decimal. We then, of course, took the natural log of that number. You want to use as many of the decimals on the calculator as you see them, and only, taking the natural log of that, only should you round in the end of the problem, the very end of the problem. So that decimal there is your k value. You could even store it in as x just to be on the safe side if you need to use that later for whatever reason. But remember, the final answer was to take this, multiply it by e, and raise it to the 20, and I'll just say 20x, keep it simple. You never want to round in the middle of a problem if you can avoid it. And that ends up being the precise decimal. And again, because we want population to be in whole numbers, we're going to actually round down to 26,461. So be careful when you're finding your k value that you actually don't round on the calculator, because if you did, in other words, if I had simply, instead of used x, let's say I had used 0.014, and I forgot my time symbol. So if you had done that instead, that would have been off pretty significantly, actually. I would suggest 26,455 or 456, I guess, if you round up, or down, I guess, to 455. Either way, I'd be okay with that. However, the problem still is you used a decimal that was rounded in the middle. This decimal is more precise. Even though we're still rounding it, it's more precise, or more accurate, I should say. This answer is not what we're wanting. So always use the decimal on your calculator as much as you possibly can without rounding, especially in the middle of a problem. Okay, let's talk about carbon dating. Carbon-14 dating assumes that carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal if the half-life of carbon-14 is 5,730 years? Okay, there should be a question mark here, but that's kind of where we're headed. We're headed with a half-life situation of which we know the actual number of years that it's going to be decaying. And this is a decay problem, obviously. Okay? So let's take a look here. Let's see how we can kind of gauge our analysis. So we're going to start off. I'm going to move my calculator over a bit. If I use my calculator, I'll get back to it. So here we can go ahead and take a look. To kick things off, first you're going to find b. And if you're wondering where b is coming from, I'm using the equation y equals, back here, y equals ae to the negative b x power, or this equation again, if you make in the actual equation itself, if b is technically negative, then b in this equation is already positive. So it ends up being in the end negative, but if this is the version we use, that'll be fine. Typically we do, actually. So right off the bat, find b, letting a equal 1 and y equals 1/2. Now if you're wondering why I'm letting a number equal, in this case a, equal to 1, I don't know how many grams, let's say, we're starting off at. So I'm going to start with 1. And if a equals 1, that means that y, half of it, in other words, decaying in half, would just be that. So here's our equation. Y equals ae to the bt power, like I said, or bx, same thing. B is going to be negative. Second step, find t. Okay, so when we go through that process, and I'm going to go ahead and denote off to the left first. I apologize. Step 2 will be to find t. But again, as far as finding our a b value, which technically you can see already taking shape, 1/2 equals 1e to the b times 5,730 power. Take the natural log of both sides, a little bit of a different methodology, and you end up with, after dividing both sides by 5,730, b to be this decimal. And then, of course, as you can see in part 2, to find t, 0.15, which is 15% of 1, equals 1 times e to that b power times t. Take the natural log, as you can see, of this, and that equals this exponent. In the end, you can solve for t, and you divide, of course, both sides by this decimal, and you end up with 15,683 years. Please try this out on your calculator as well.